A mantle plume is a mechanism proposed in 1971 to explain volcanic regions of the Earth that were not thought to be explicable by the then new theory of plate tectonics. Some such volcanic regions lie far from tectonic plate boundaries, for example, Hawaii. Others represent unusually large volume volcanism, whether on plate boundaries, e.g. Iceland, or basalt floods such as the Deccan or Siberian traps. A mantle plume is posited to exist where hot rock nucleates at the core mantle boundary and rises through the Earth's mantle, becoming a diapirine, the Earth's crust. The currently active volcanic centers are known as hotspots. In particular, the concept that mantle plumes are fixed relative to one another and anchored at the core mantle boundary was thought to provide a natural explanation for the time-progressive chains of older volcanoes seen extending out from some such hotspots, such as the Hawaiian Emperor Sea Mount chain. The hypothesis of mantle plumes from depth is not universally accepted as explaining all such volcanism. It has required progressive hypothesis elaboration leading to variant propositions such as mini-plumes and pulsing plumes. Another hypothesis for unusual volcanic regions is the plate model. This proposes shallower, passive leakage of magma from the mantle onto the Earth's surface where extension of the lithosphere permits it, attributing most volcanism to plate tectonic processes, with volcanoes far from plate boundaries resulting from intraplate extension. Concepts. In 1971, geophysicist W. Jason Morgan proposed the hypothesis of mantle plumes. In this hypothesis, convection in the mantle transports heat from the core to the Earth's surface in thermal diapirs. In this concept, two largely independent convective processes occur in the mantle: the broad convective flow associated with plate tectonics, which is driven primarily by the sinking of cold plates of lithosphere back into the mantle asthenosphere, and mantle plumes, which carry heat upward in narrow, rising columns, driven by heat exchange across the core mantle boundary. The latter type of convection is postulated to be independent of plate motions. The sizes and occurrence of mushroom mantle plumes can be predicted easily by transient instability theory developed by Tan and Thor. The theory predicts mushroom mantle plumes of about 2,000 kilometers diameter with a critical time of about 830 MYR for a core mantle heat flux of 20 milliwatts per square meter, while the cycle time is about 2 GeA. The number of mantle plumes is predicted to be about 17. The plume hypothesis was studied using laboratory experiments conducted in small fluid-filled tanks in the early 1970s. Thermal or compositional fluid dynamical plumes produced in that way were presented as models for the much larger postulated mantle plumes. On the basis of these experiments, mantle plumes are now postulated to comprise two parts: a long thin conduit connecting the top of the plume to its base, and a bulbous head that expands in size as the plume rises. The entire structure is considered to resemble a mushroom. The bulbous head of thermal plumes forms because hot material moves upward through the conduit faster than the plume itself rises through its surroundings. In the late 1980s and early 1990s, experiments with thermal models showed that as the bulbous head expands, it may entrain some of the adjacent mantle into the head. When a plume head encounters the base of the lithosphere, it is expected to flatten out against this barrier and to undergo widespread decompression, melting to form large volumes of basalt magma. It may then erupt onto the surface. Numerical modeling predicts that melting and eruption will take place over several million years. These eruptions have been linked to flood basalts, although many of those erupt over much shorter time scales. Examples include the Deccan traps in India, the Siberian traps of Asia, the Karoo basalts, dolerites in South Africa and Antarctica, the Piranha and Atondaca traps in South America and Africa, and the Columbia River basalts of North America. Flood basalts in the oceans are known as oceanic plateaus, and include the Ontong-Java Plateau of the Western Pacific Ocean and the Kerguelen Plateau of the Indian Ocean. The narrow vertical pipe, or conduit, postulated to connect the plume head to the core mantle boundary, is viewed as providing a continuous supply of magma to a fixed location, often referred to as a hotspot. As the overlying tectonic plate moves over this hotspot, the eruption of magma from the fixed conduit onto the surface is expected to form a chain of volcanoes that parallels plate motion. The Hawaiian Islands chain in the Pacific Ocean is the type example. Interestingly, it has recently been discovered that the volcanic locus of this chain has not been fixed over time, and it thus joined the club of the many type examples that do not exhibit the key characteristic originally proposed. The eruption of continental flood basalts is often associated with continental rifting and breakup. This has led to the hypothesis that mantle plumes contribute to continental rifting and the formation of ocean basins. In the context of the alternative plate model, continental breakup is a process integral to plate tectonics. A massive volcanism occurs as a natural consequence when it onsets. The current mantle plume theory is that material and energy from Earth's interior are exchanged with the surface crust in two distinct modes. The predominant, steady-state plate tectonic regime driven by upper mantle convection and a punctuated, intermittently dominant, mantle overturn regime driven by plume convection. This second regime, while often discontinuous, is periodically significant in mountain building and continental breakup. Chemistry, heat flow and melting. The chemical and isotopic composition of basalts found at hotspots differs subtly from mid-ocean ridge basalts. This geochemical signature arises from the mixing of near-surface materials such as subducted slabs and continental sediments in the mantle source. There are two competing interpretations for this. In the context of mantle plumes, the near-surface material is postulated to have been transported down to the core mantle boundary by subducting slabs, and to have been transported back up to the surface by plumes. In the context of the plate hypothesis, subducted material is mostly recirculated in the shallow mantle and tapped from the bivolcanoes. The processing of oceanic crust, lithosphere, and sediment through a subduction zone decouples the water-soluble trace elements from the immobile trace elements, concentrating the immobile elements in the oceanic slab. Seismic tomography shows that subducted oceanic slabs sink as far as the bottom of the mantle transition zone at 650 kilometers depth. Subduction to greater depths is less certain, but there is evidence that they may sink to mid-lower mantle depths at about 1,500 kilometers depth. The source of mantle plumes is postulated to be the core mantle boundary at 3,000 kilometers depth. Because there is little material transport across the core mantle boundary, heat transfer must occur by conduction, with adiabatic gradients above and below this boundary. The core mantle boundary is a strong thermal discontinuity. The temperature of the core is approximately 1,000 degrees Celsius higher than that of the overlying mantle. Plumes are postulated to rise as the base of the mantle becomes hotter and more buoyant. Plumes are postulated to rise through the mantle and begin to partially melt on reaching shallow depths in the asthenosphere by decompression, melting. This would create large volumes of magma. The plume hypothesis postulates notes that this melt rises to the surface and erupts to form hot spots. The lower mantle and the core. The most prominent thermal contrast known to exist in the deep mantle is at the core mantle boundary. Mantle plumes were originally postulated to rise from this layer because the hotspots that are assumed to be the surface expression were thought to be fixed relative to one another. This required that plumes were sourced from beneath the shallow asthenosphere that is thought to be flowing rapidly in response to motion of the overlying tectonic plates. There is no other known major thermal boundary layer in the deep earth, and so the core mantle boundary was the only candidate. The base of the mantle is known as the D layer of seismological subdivision of the Earth. It appears to be compositionally distinct from the overlying mantle, and may contain partial melt. Two very large large low-shear velocity provinces exist in the lower mantle under Africa and under the Central Pacific. It is postulated that small plumes rise from the surface of their edges. Their low seismic velocities were thought to suggest that they are relatively hot, although it has recently been shown that the low wave velocities are due to high density caused by chemical heterogeneity. Evidence for the theory. Various lines of evidence have been cited in support of mantle plumes. There is some confusion regarding what constitutes support, as there has been a tendency to redefine the postulated characteristics of mantle plumes after observations have been made. Some common and basic lines of evidence cited in support of the theory are linear volcanic chains, noble gases, geophysical anomalies and geochemistry. Linear volcanic chains. The age-progressive distribution of the Hawaiian Emperor Sea Mount chain has been explained as a result of a fixed, deep mantle plume rising into the upper mantle, partly melting, and causing a volcanic chain to form as the plate moves overhead relative to the fixed plume source. Other hotspots with time-progressive volcanic chains behind them include e.g.Iceland Union and the Lacadivus Chagos Ridge, the Louisville Seamount chain, the 90 East Ridge and Kerguelen, Tristan da Cunha, and Yellowstone. An intrinsic aspect of the plume hypothesis is that the hotspots and the volcanic trails have been fixed relative to one another throughout geological time. Whereas there is evidence that the chains listed above are time-progressive, it has, however, been shown that they are not fixed relative to one another. The most remarkable example of this is the Emperor chain, the older part of the Hawaii system, which was formed by a migration of volcanic activity across a geostationary plate. Many postulated hotspots are also lacking time-progressive volcanic trails, e.g. Iceland, the Galapagos, and the Azores. Mismatches between the predictions of the hypothesis and observations are commonly explained by auxiliary processes such as mantle wind, ridge capture, ridge escape, and lateral flow of plume material, noble gas and other isotopes. 3. He is considered a primordial isotope as it was formed in the Big Bang. Very little is produced, and little has been added to the Earth by other processes since then. 4. He includes a primordial component, but it is also produced by the natural radioactive decay of UNTH. Over time, he in the upper atmosphere is lost into space. Thus, the Earth has become progressively depleted in heat. And 3. He is not replaced as 4. He is. As a result, the ratio 3 heat 4 he in the Earth has lowered over time. Unusually high 3 heat 4 he have been observed in some, but not all, hotspots. In mantle plume theory, this is explained by plumes tapping a deep, primordial reservoir in the lower mantle, where the original high 3He/4 He ratios have been preserved throughout geologic time. In the context of the plate hypothesis, the high ratios are explained by preservation of old material in the shallow mantle. Ancient high 3He/4 He ratios would be particularly easily preserved in materials lacking U/Th, so 4 He was not added over time. Olivine and dunite, both found in subducted crust, are materials of this sort. Other elements, e.g. osmium, have been suggested to be traces of material arising from near to the Earth's core, in basalts at oceanic islands. However, so far conclusive proof for this is lacking. Geophysical anomalies. The Plume hypothesis has been tested by looking for the geophysical anomalies predicted to be associated with them. These include thermal, seismic, and elevation anomalies. Thermal anomalies are inherent in the term hotspot. They can be measured in numerous different ways, including surface heat flow, petrology, and seismology. Thermal anomalies produce anomalies in the speeds of seismic waves, but unfortunately sudden decomposition and partial melt. As a result, wave speeds cannot be used simply and directly to measure temperature, but more sophisticated approaches must be taken. Seismic anomalies are identified by mapping variations in wave speed as seismic waves travel through Earth. A hot mantle plume is predicted to have lower seismic wave speeds compared with similar material at a lower temperature. Mantle material containing a trace of partial melt, or being richer in Fe, also has a lower seismic wave speed, and those effects are stronger than temperature. Thus, although unusually low wave speeds have been taken to indicate anomalously hot mantle beneath hotspots, this interpretation is ambiguous. The most commonly cited seismic wave speed images that are used to look for variations in regions where plumes have been proposed come from seismic tomography. This method involves using a network of seismometers to construct three-dimensional images of the variation in seismic wave speed throughout the mantle. Seismic waves generated by large earthquakes enable structure below the Earth's surface to be determined along the ray path. Seismic waves that have traveled 1,000 or more kilometers can be used to image large regions of Earth's mantle. They also have limited resolution, however, and only structures at least several hundred kilometers in diameter can be detected. Seismic tomography images have been cited as evidence for a number of mantle plumes in Earth's mantle. There is, however, vigorous ongoing discussion regarding whether the structures imaged are reliably resolved, and whether they correspond to columns of hot rising rock. The mantle plume hypothesis predicts that domal topographic uplifts will develop when plume heads impinge on the base of the lithosphere. An uplift of this kind occurred when the North Atlantic Ocean opened about 54 million years ago. Some scientists have linked this to a mantle plume postulated to have caused the breakup of Eurasia and the opening of the North Atlantic, now suggested to underlie Iceland. Current research has shown that the time history of the uplift is probably much shorter than predicted. However, it is thus not clear how strongly this observation supports the mantle plume hypothesis. Geochemistry. Basalts found at oceanic islands are geochemically distinct from those found at mid-ocean ridges and volcanoes associated with subduction zones. Ocean island basalt is also similar to basalts found throughout the oceans on both small and large seamounts. They are also compositionally similar to some basalts found in the interiors of the continents. In major elements, ocean island basalts are typically higher in iron and titanium than mid-ocean ridge basalts at similar magnesium contents. In trace elements, they are typically more enriched in the light rare earth elements than mid-ocean ridge basalts. Compared compared to island arc basalts. Ocean island basalts are lower in alumina and higher in immobile trace elements. These differences result from processes that occur during the subduction of oceanic crust and mantle lithosphere. Oceanic crust typically becomes hydrated to varying degrees on the seafloor, partly as the result of seafloor weathering, and partly in response to hydrothermal circulation near the mid-ocean ridge crest where it was originally formed. As oceanic crust and underlying lithosphere subduct, water is released by dehydration reactions, along with water-soluble elements and trace elements. This enriched fluid rises to metasomatize the overlying mantle wedge and leads to the formation of island arc basalts. The subducting slab is depleted in these water-mobile elements and thus relatively enriched in elements that are not water-mobile compared to both mid-ocean ridge and island arc basalts. Ocean island basalts are also relatively enriched in immobile elements relative to the water-mobile elements. This, and other observations, have been interpreted as indicating that the distinct geochemical signature of ocean island basalts results from inclusion of a component of subducted slab material. This must have been recycled in the mantle, then remelted and incorporated in the lavas erupted. In the context of the Plume hypothesis, subducted slabs are postulated to have been subducted down as far as the core mantle boundary, and transported back up to the surface in rising plumes. In the plate hypothesis, the slabs are postulated to have been recycled at shallower depths, in the upper few hundred kilometers that make up the upper mantle. However, the plate hypothesis is inconsistent with both the geochemistry of shallow asthenosphere melts and with the isotopic compositions of ocean island basalts. Seismology. In 2015, based on data from 273 large earthquakes, researchers compiled a model based on whole waveform tomography, requiring the equivalent of 3 million hours of supercomputer time. Due to computational limitations, high-frequency data still could not be used, and seismic data remained unavailable from much of the seafloor. Nonetheless, vertical plumes 400 c hotter than the surrounding rock were visualized under many hotspots, including the Pitcairn, McDonald, Samoa, Tahiti, Marquesas, Galapagos, Cape Verde, and Canary hotspots. They extended nearly vertically from the core mantle boundary to a possible layer of shearing and bending at 1,000 kilometers. They were detectable because they were 600 to 800 kilometers wide, more than 3 times the width expected from contemporary models. Many of these plumes are in the large, low shear velocity provinces under Africa and the Pacific, while some other hotspots such as Yellowstone were less clearly related to mantle features in the model. The unexpected size of the plumes leaves open the possibility that they may conduct the bulk of the Earth's 44 terawatts of internal heat flow from the core to the surface, and means that the lower mantle convects less than expected, if at all. It is possible that there is a compositional difference between plumes and the surrounding mantle that slows them down and broadens them. Suggested mantle plume locations. Many different localities have been suggested to be underlain by mantle plumes, and scientists cannot agree on a definitive list. Some scientists suggest that several tens of plumes exist, whereas others suggest that there are none. The theory was really inspired by the Hawaiian volcano system. Hawaii is a large volcanic edifice in the center of the Pacific Ocean, far from any plate boundaries. Its regular, time-progressive chain of islands and seamounts superficially fits the plume theory well. However, it is almost unique on Earth, as nothing as extreme exists anywhere else. The second strongest candidate for a plume location is often quoted to be Iceland, but this lies on a spreading plate boundary. and its massive nature can be equally explained by a combination of plate tectonic forces. Mantle plumes have been suggested as the source for flood basalts. These extremely rapid, large-scale eruptions of basaltic magmas have periodically formed continental flood basalt provinces on land and oceanic plateaus in the ocean basins, such as the Deccan traps, the Siberian traps, the Kara flood basalts of Gondwana, and the largest known continental flood basalt, the Central Atlantic Magmatic Province. Others have pointed out the coincidence of many continental flood basalt events with continental rifting. This is consistent with a system that tends toward equilibrium as matter rises in a mantle plume. Other material is drawn down into the mantle, causing rifting. Alternate hypotheses. In parallel with the mantle plume model, two alternative explanations for the observed phenomena have been considered: the plate hypothesis and the impact hypothesis. The plate hypothesis. The plate hypothesis suggests that anomalous volcanism results from lithospheric extension that permits melt to rise passively from the asthenosphere beneath. It is thus the conceptual inverse of the plume hypothesis, attributing volcanism to shallow, near-surface processes associated with plate tectonics, rather than active processes arising at the core mantle boundary. The plate hypothesis embodies the concept that deep mantle plumes causing surface-time progressive volcanism do not exist. Lithospheric extension is attributed to processes related to plate tectonics. These processes are well understood at mid-ocean ridges, where most of Earth's volcanism occurs. It is less commonly recognized that the plates themselves deform internally, and can permit volcanism in those regions where the deformation is extensional. Well-known examples are the Basin and Range Province in the western USA, the East African Rift Valley, and the Rhine-Graben. Variable fertility in the source region, usually the mantle, results in variable volumes of magma being produced. The ocean island basalt geochemistry of lavas found at many places, and attributed to plumes bullshit, in fact, a geochemical signature of enhanced fertility in the melt source. The plate hypothesis thus attributes all of Earth's volcanism to a single process, plate tectonics, rather than to two independent processes, but does not address issues of core mantle heat and/or material transfer. Under the umbrella of the plate hypothesis, the following sub-processes, all of which can contribute to permitting surface volcanism, are recognized: continental breakup, fertility at mid-ocean ridges, enhanced volcanism at plate boundary junctions, small-scale sublithospheric convection, oceanic intraplate extension, slab tearing and break-off, shallow mantle convection, abrupt lateral changes in stress at structural discontinuities, continental intraplate extension, catastrophic lithospheric thinning, sublithospheric melt ponding and draining. The impact hypothesis. In addition to these processes, impact events such as ones that created the Adams crater on Venus and the Sudbury igneous complex in Canada are known to have caused melting and volcanism. In the impact hypothesis, it is proposed that some regions of hotspot volcanism can be triggered by certain large-body oceanic impacts which are able to penetrate the thinner oceanic lithosphere, and flood basalt volcanism can be triggered by converging seismic energy focused at the antipodal point opposite major impact sites. Impact-induced volcanism has not been adequately studied and comprises a separate causal category of terrestrial volcanism with implications for the study of hotspots and plate tectonics. Comparison of the hypotheses. In 1997 it became possible using seismic tomography to image submerging tectonic slabs penetrating from the surface all the way to the core mantle boundary. For the Hawaii hotspot, long-period seismic body wave diffraction tomography provided evidence that a mantle plume is responsible, as had been proposed as early as 1971. For the Yellowstone hotspot, seismological evidence began to converge from 2011 in support of the plume model, as concluded by James et al. We favor a lower mantle plume as the origin for the Yellowstone hotspot. Data acquired through EarthScope, a program collecting high-resolution seismic data throughout the conterminous United States, has accelerated acceptance of a plume underlying Yellowstone. Although there is strong evidence that at least two deep mantle plumes rise to the core mantle boundary, confirmation that other hypotheses can be dismissed may require similar tomographic evidence for other hotspots.